Today. I'm Amal Khili, a data science engineer and co-founder of PyLadies Tunis, along with Mona Belaid, a business intelligence and data consultant, and Hediat Nani, a data analyst. I will present now PyLadies. We are among a network of Python practitioners in Tunis, Tunisia. We are very passionate about the Python programming. In fact, PyLadies Tunis is part of PyLadies global community. We are an international mentorship group that helps people become active participants and leaders, especially women, in the Python open source community. We are very proud that our community is growing day by day. In fact, we have like 76 chapters with over 50,000 members located in 29 countries and 74 cities. Our mission is to promote, educate, and advance a diverse Python community through outreach, education, conferences, events, and social gathering. Also, PyLadies aims to provide a friendly support network for women and for everyone, and a bridge to the larger Python world. Anyone with an interest in Python is encouraged to participate. Thank you again, and now I will let Hedia present our speaker.
Thank you, Amal. So I'm very honored today to have with us David De La Iglesia, who will show us how to build an MLOps workflow. David is a software engineer at Iterative, where he mainly works on open source tools like DUVC and DUVC Live. Before that, he was a senior computer vision researcher at Gradient. Thank you, David, for accepting our invitation. And the screen is yours.
Yeah, thanks for inviting me, and thank you all for coming. Yeah, we try to share. Okay, can you all see my screen?
Yes.
Yes, thank you.
All right. Yeah, thanks, Hedia, for the introduction. So today we are going to talk, like Hedia mentioned, about how to build an MLOps workflow using GitHub and Git as basic tools, and try to expand their capabilities with DBC and CML and other tools that I work on. So, as Hedia said before, my name is David. I work as software engineer in Iterative.ai. So the idea first is a very small introduction to what is MLOps. Then we are going to cover what problem we are trying to solve from a machine learning perspective and how we can expand this machine learning project to embrace MLOps practices. And then we jump into a hands-on workshop, which is the main idea. So MLOps, to be honest, I work as a software engineer building MLOps tools, and I don't really know what it is, mainly because it's very dependent on the use case of the person that needs MLOps. So I remember when I was a computer vision researcher, one day my boss kind of asked me just like that, if I could like try to embrace MLOps best practices. So I had to go in this quest of discovering what this means. And the first thing I find is end-to-end ML platforms. Mainly, practically any cloud provider has one MLOps platform. And as I checked how it worked, the main issues I think that this platform had was that, first of all, it could be some kind of overkill depending on the size of the project. So it didn't make sense to me to launch this enormous platform and combination of services only to train a very simple model on a very small data set. But you didn't have any choice. Like if you use this platform, you have to use the full equipment. Then the thing that I didn't like was that it feels to me that these platforms isolate the researchers or the person working with machine learning models from software engineering best practices, because these platforms live in services isolated from the tools that software engineers use in day-to-day, like GitHub or Git. So these platforms are kind of disconnected from these other platforms. And the problem is also that if once you pick one of these platforms, it's not really easy to switch, because you have to start building some custom components to connect to this platform. So it's very tricky once you pick one to switch to other. So I didn't like that, because I don't want to, perhaps some platform is not the best suite for some project. And especially if you want to integrate some other tool that doesn't belong to the cloud platform, then it's very tricky to do, even impossible in many times. So an alternative to this is to go yourself and try to build an MLOps platform using open source components. And the issue I found here with this approach is that the MLOps world is so populated by so many different tools doing so many different things that it was non-trivial to find out how to connect these pieces, or even how to understand what these tools do. Yeah. So my idea was try to take a step back and think about what is the end purpose of MLOps, and asking around to other researchers and to myself, what I find is that the main focus of MLOps should be to make the life of the researcher easier, such as if the researcher goes away on vacation, there is no problem if new data arise, because the model can be retrained, evaluated, and deployed easily, even automatically, even if the researcher is not around. So the researcher should be able to focus only on researching, not on maintaining the infrastructure. And if he goes on vacation, he can like chill out and don't have to answer calls, because this new data set arrived and the model needs to be trained, and only the researcher knows how to orchestrate all this. So that's the second part, which is eventually this researcher is going to leave the company, and some other people needs to pick up the project they left. And this happens to me that I have to go and try to revive some project from other researchers that left, and the lack of documentation or lack of just how the project was set up made me, it was very difficult for me to try to catch up with the project state. So another goal for MLOps should be that this should not happen, that if a researcher leaves or disappears, any other researcher can pick up this project and be able to continue without many efforts. So the problem we are going to try to work around in this workshop is an automatic issue labeler. So to give you an example, I work on the DBC project, which is open source and is on GitHub, and we have over 3,000 over 3,000 issues in total between open and close. And we have a tons of useful labels that we use to label these issues, so we can decide who can take the issue, how important it is. So it's important that the issues are, there is an easy way to identify to which component of DBC these issues relate to. So I think it would be fun to try to build a machine learning model that predicts an appropriate label for an issue. And apart from that, try to expand the project to embrace MLOps best practices, but coming from this goals first perspective. So with this, I am going to just jump on the project and our solution. So we have a data source repository which in this case is the DBC repository, where people open issues every day, and someone needs to label those issues and assign a proper label about whether it is a feature request, a bug report, and to which component or components of DBC it's related. So from that data source, we are going to try to build a data set which is different from our raw data, because we have the data set has to have a specific format that the machine learning framework expects. And with that data set, we are going to train a machine learning model. In this case, we are going to use the Hugging Face framework. And once we have a model trained, we are going to deploy it by using Docker directly on the GitHub repository of DBC. So the model can label issues automatically. And to do that, we are going to work on a single repository, which is going to be in GitHub, and we are going to use DBC and CML tools to try to orchestrate these MLOps best practices so we can ensure reproducibility and automation of this workflow. So here's the link of the repository where the steps of the workshop are described. And I also added a separate link with the final solution once you have followed all the steps. So how your repo should look once you follow all the steps defined in here. So I would like to, are there any questions up to this point before we jump into this hands-on workshop?
For the moment, no. Can you put in the chat so we can share with the participant links?
Yeah.
Thank you.
Maybe I can share the solution also. I don't know if I shared in the right chat. Do you get the link?
Yeah, we are putting it on YouTube. It's
okay.
Good.
Nice. So here is our initial repository, so the initial state, where we already have a functioning pipeline that trains a model, but now we are going to try to take this to the next level by incorporating MLOps best practices. So we are going to use DBC, as I mentioned, also DBC Live, which is a separate library, and CML and Transformers. So the project is based mainly around these libraries.
Sorry, so David, the font is really very, very small. Yeah, thank you.
How about now?
Yeah, it's good. Thank you.
Oh, okay. So yeah, like I said, there are some links to the tools we are going to base our workflow on. Feel free to give a GitHub start. So the current state before any MLOps is that we have a DBC pipeline, which we define in a DBC YAML file. This pipeline is composed of many stages. So we are already in a very good shape because we have separated each logical component of our workflow in separate scripts, Python scripts in this case, because we are in PyLadies workshop. But DBC actually can reproduce stages from any language. It's not really Python restricted. So we have a first stage that is going to fetch or get the data from the DBC repository. We are going to compute some data metrics, like try to count the number of issues for each label. Then we are going to separate the data into train and validation splits. We are going to train the model, and once we have a training model, we are going to evaluate the model using one of the splits we generate before. So a DBC YAML file looks like this, and it's the font okay, by the way? Is the font big enough?
Yes, it's okay.
Okay, thank you.
Thank you.
So DBC pipeline is defined in this DBC YAML file, which has a very simple format. You have to define a list of stages and assign them some name, in this case, get data. Then you need to indicate which command you want to run in this stage. Like I said before, we're going to run Python scripts. So we call Python targeting this script that is in charge of fetching data from the GitHub repository. And we indicate an output folder, which has this weird, strange syntax that I am going to explain later. We indicate which dependencies this stage has. So DBC is going to look to this the list of dependencies, and if there are some changes in between the last time you run the pipeline and the current one, then DBC knows that it has to rerun this stage. So if we have our pipeline and we change something in the dependency of the training stage, DBC is not going to rerun the stages before because nothing has changes there. So it's only going to rerun the train and the evaluation stage. This is a cool feature that allows you to save computation by taking care of tracking and rerunning only the parts that are needed. So apart from dependencies, DBC also supports to indicate some params or parameters that this stage depends on. So DBC params are defined in a separate file called params.yaml, and it has a very simple structure like before, where you can optionally define sections to keep the parameters organized. So in this case, we are indicating that the get data stage depends on the parameters repo, labels, signs, since, and until. And these parameters are defined here. So instead of having these variables hard-coded in our Python script, what we do is we extract the values to this separate file, params.yaml, and we link the params.yaml and the Python script using DBC. So if someone changes up the value of this parameter in the params.yaml file, DBC knows that this stage needs to be rerun. And finally, we say where DBC is going to store the outputs. So this syntax is a special syntax that DBC uses, and what it does is that DBC will try to look for this value in params.yaml, so data, output folder, and will interpolate the value into this command invocation. So this is the same as if we call this script with this value hard-coded, but like we said, it's a good practice to decouple this and move the parameters to a single point where you can track all your options. Okay. This was the get data, and this is defined in the src folder. We are not going to dive into what this script does, because you can check it out later. What you need to know is that it uses these parameters to know which labels it needs to fetch from the GitHub repo, and the data in between those labels, those issues are relevant. So we are indicating that we only want issues between the first day of 2021 and 2 days ago. Then we have a very small stage that computes data metrics, which is this one. And this is how DBC knows that this stage depends on the previous one, is that because we indicate that as a dependency, we have the output folder or of the first stage. So this stage has this as output, and this stage has the same thing as dependency. So DBC knows that this is a link that he should know about in order to rerun the stage if anything changed. So this stage is very simple. What it does is that once you have fetched all the data from GitHub, it's going to count how many labels are of each of these three. Okay. This stage is not connected to anything else because that's where these metrics are not necessary for any of the other stages. So next stage is called split data. And like before, it depends on the first stage output, and it generates a new output where basically we have divided the full dataset into two splits, one for training and one for validation. And this is done by using scikit-learn or the train test splits function. So like I said before, this script is very simple. We are not going to dive into. You can check it out later. All you need to know is that this script takes the input of the first stage and splits the dataset into train and validation splits. Okay, so that is why it's connected to get data. So once we have this splitted dataset, we can jump into the train script or train stage, which uses Hugging Face to train a model from these splits of train and validation. You can check it out later, but Hugging Face is makes it very simple to train a model. And it has a very good course that I encourage you to take if you want to learn more how this framework works. But all you need to know for now is that the Python train stage runs the Python train script. It depends on the output folder of the script of the split stage, and it has some parameters and outputs, and it generates metrics and plots. So this is another interesting part, which is that some of these stages, like the compute data metrics, split data, train, and evaluation, generates DBC metrics and DBC plots. So DBC metrics and DBC plots are just plain text files. So you can track those with Git, and they look like this. So you have this is useful to track the performance of the model, and it's good that you have it tracked on your Git repo because it's connected with the current state of the pipeline. So the final stage is evaluation, and it takes the model trained by Hugging Face and the split of validation and generates some new metrics which are stored in a confusion matrix in this case. So this format is a plain JSON file, and it's kind of tricky to visualize, but the good thing is that it's on GitHub, so you can check the values associated to each commit. So this state is a very good starting point, even if we don't have any MLOps, because DBC pipelines can be reproduced with a single command. And if you change something, DBC knows what parts of the pipeline need to be reproduced and which parts don't. So it saves computation. So the good thing is that in Iterative, we have been also developing this UI for taking a look at these DBC metrics and plots in a nicer way. So this studio view, I left the link here of the product, is free to use up to 2 members, and yeah, it allows you to connect to GitHub. So this is how it looks in Studio, my GitHub repository, which has already followed the workshop. That's why there are so many commits and branches. But as you can see, so you have some columns colored for metrics, which is the same. It has the same content as the JSON file, but you can look it in a table, so it's nicer to differentiate in between commits. And you also have your parameters and information about your data files. In addition to that, the plots that we have been generating, which are stored, for example, in this case, in plain TSV files, like this, you can visualize in Studio, and those plots get rendered as graphs. And you can have custom plots like confusion matrix, and you can also log images that will be shown here. So this is just a heads up to check Studio. If you have been using DBC or you're going to start using DBC, it's a good way to connect your Git repository where you are using and DBC and generating DBC outputs like metrics and plots. And it allows you to visualize the whole picture of the project in a nicer way. So this is the current state of the of this project before we are even starting to implement MLOps best practices. So is there any question up to this point?
I don't see any. So please, can you write if you have any question?
Yeah. Sorry. Okay. Yeah, feel free to write any question even during the workshop. So that's the current state. It's a very good one to begin with because we have reproducibility at the local level. So if someone clones this repository, he can run DBC repro and he can send the changes through GitHub. So now, to get started with this MLOps approach, the first thing we need to know is that when we are training a model with this DBC pipeline or just by running Python scripts, we are going to generate some files that are too large to be tracked by Git. So probably you don't want to commit and send to GitHub a model that takes 100 megabytes of space, and you also don't want to commit your full data set, which can take even more space. So DBC extends the capabilities of Git and GitHub by providing what is called a DBC Remote. So DBC Remotes allow you to store arbitrarily large artifacts like models or data sets, and you can pick up, you can use as remote storage basically any cloud provider. So these DBC remotes work the same for any cloud, so we can say that it's cloud agnostic. In this case, I choose to use Google Drive because it's easier to set up, and this is a very small data set and very small model, so it doesn't require much space. The good thing is that any command from DBC is going to work the same no matter where you put your data. So even if I start this project using Google Drive, and if I later want to change the remote to Amazon S3 bucket, all the commands and all the pipeline can be run the same. So DBC abstract us from having to care about how these different cloud providers work. So in order to add a provider, remote, what you need to do is that if you are from the website, you can go and create and update the content of DBC of the .dbc/config file. In this file, what we say is that we are using a remote called myremote, and the URL is a Google Drive / syntax in order to differentiate that this is a Google Drive remote. And this URL is just the URL that you can find in your Drive storage once you create a folder. So in this case, I have this folder, which is already filled with things by DBC because this is the solution folder. And this URL is what I have writing here. So this is the way that you indicate DBC that that's the Google Drive folder where you want to store your artifacts. If you are using the CLI tool, all you need to do is run this command. When you say DBC remote add, we indicate that this is going to be our default remote, and we just pass this Google Drive syntax and the URL that I just copy from here. So with this, now we can run DBC push and DBC pull commands in order to upload our artifacts to the DBC remote. In this case, we can enable, we are going from local reproducibility to shared reproducibility. So let's say that this researcher on his local machine runs DBC repro after having updated some hyperparameter, and it adds the changes to Git and push the changes to Git. So the Git track files, like the source files, are going to be pushed to the GitHub repository, and the large artifacts are going to be pushed to the DBC remote. All it gets DBC to know what the artifacts are associated to this specific commit is this file called DBC log. Sorry, that it gets auto-generated once you root the pipeline. So this file gets pushed to GitHub, and the artifacts references by custom hashes are stored in the Google Drive repository. So now, if other researcher from other machine runs git pull and DBC pull, it is going to fetch all the DBC pipeline changes from GitHub and all the DBC artifacts from the remote. So this way you can share your model and dataset with others and enable shared reproducibility. So this is a very good first step towards MLOps, which is that now all the things needed to reproduce the pipeline are not in someone's computer, but they are both stored on the one hand on the GitHub repository and on the other hand on the DBC remote, the large artifacts. Okay, so this is a good step forward towards, but the ideal scenario would be that anyone should be able to reproduce the pipeline even without requiring to install DBC and all the requirements in his own machine. So to do that, we first need to grant access to the DBC remote from GitHub. So if you are in a local computer, the first time you run one of these commands, DBC pull or DBC push, DBC is going to ask you for credentials to authenticate to this remote. Okay, But from GitHub, in order to enable running this pipeline from GitHub Actions, you need to grant GitHub access to the DBC Remote. So in order to do this, I share with you here a Google Collab where you can copy-paste your Google Drive URL and paste it here.
Sorry, can you make it bigger?
Yeah.
And
So,
then we have one question.
Okay. So let me finish this and,
yeah.
and I take the question. So this
Okay.
is just in order to generate this special JSON that we are going to store in GitHub in order to allow GitHub to connect to our DBC remote. So yeah, let me take the question then. So what's the question? Sorry. Oh, I can see.
Okay. So the question is, this solution, is it MLOps level 1 or 2?
I am not sure what these levels mean. Could you please elaborate?
Okay, Abir, could you please explain what's level 1 or level 2 means?
I'm going to drink 1 second because I am talking too much.
Yeah, okay.
Well, if Abir adds more details, feel free to interrupt me. Otherwise, I'm going to try to continue.
Okay, thank you.
Okay, so this collab that I share is just an easy way of getting the credentials for your remote. In the DBC documentation, you can find how to get the right credentials for all the supported remote types. As you can see from this list, we pretty much support any cloud provider, major cloud provider, and we are also allowed to set up some SSH remotes, HTTP remotes, so pretty much anything. The important part is that this code is going to work no matter what type of remote you are using. Okay, so in my solution repo, what I have been doing with that Google Collab is I created a GitHub secret called head credentials data using the content generated from the Google Collab. This allows GitHub to have access to my DBC. So when I run something on GitHub Actions, I can run this DBC pull and DBC push commands, and everything gets connected to the DBC remote. Okay. So once GitHub has access to our DBC remote, just like our fellow researcher, we can create a workflow, GitHub workflow, that is going to be triggered every time we create a pull request, and we also allow to run this workflow on demand. So this is just another YAML file, which in this case is a GitHub Actions YAML, which has a syntax very similar in some ways to DBC YAML, where we define a sequence of steps that we want this workflow runner to perform. The important thing here is that what we are going to do in this workflow would be very similar to what this fellow researcher would need to do in his machine. But by doing and implementing this GitHub workflow, anyone with access to the GitHub repository can trigger this workflow in order to run the full pipeline. So we obviously need to first install all requirements needed to train this, and we run this DBC repro pull command that is going to try to fetch any data from the DBC remote required in order to run the pipeline. If it doesn't find any data on the remote, then it's going to just run the pipeline like it was the first time. So this DBC repro would be the same that researcher A was running in his computer, but in this case, it's going to be run in this GitHub computer that is provided to us every time we run workflow. So because we have granted GitHub with access to our DBC remote, we can push the changes to the DBC remote. So after this pipeline has been run, all the changes are available for anyone with access to the remote. Because we also have changes to be tracked by Git, this can be a little tricky to do, because when you are running this locally, you can run this git add and git commit and git push commands, but it's more tricky to do this inside a GitHub workflow. This is the first time we are going to use CML, which is another open source tool made by Iterative, and it provides a series of utilities. One of those is called CML PR, and what it does is that it receives what files do we want to track with Git, and it's going to create a new GitHub pull request targeting our branch where this pipeline has been triggered. So the difference is that when you are running locally, you have access to Git commands and you are working on your local Git repository. But when you are working in this GitHub Actions workflow, it's no longer your computer. You still need to share the changes and push the changes to GitHub. And CML provides you with this utility function that instead of adding and committing and pushing directly to a branch, it creates a separate pull request that you can accept in order to merge these changes. Because not every time you want to merge the changes in your main branch, for example, if the training has not been successful. So after that, another utility that CML provides is this CML send comment function that allows you to post a custom markdown report in the PR that was created before. So let me show you how this looks. So in this solution, we have some PRs generated by CML. Sorry, these PRs generated by GitHub. And on these PRs, we can see a CML report that was sent with this function, generated with this function, combined with some DBC utility report. For example, DBC generates this table in Markdown format, and CML sends the content to this PR. We can see now all metrics and parameters related to the experiment run in this branch, and the difference between the main branch and or the current workspace, which is the new experiment. In addition, we also are able to take a look at the plots comparing the current workspace and the previous state. So this is CML send comment utility. Like you can see that this step is kind of complicated, and we are working on the DBC Live library with a functionality to auto-generate these reports directly from the training framework, so you don't have to add this all these steps to your GitHub workflow. So this is a GitHub workflow that will be run on pull request or manually. With this, we have enabled a way to reproduce the pipeline from pretty much anywhere where you have access to internet. So if we are in GitHub, we can go to, so we are in the GitHub repository where this workflow exists, and we go and try to change any parameter in the pipeline. So we are going to train for 8 epochs instead of 15. And if we create a PR saying that we have changed epochs to 8, we create a new pull request, and this will trigger this workflow that we defined before, because we indicate that we want to trigger this workflow on PR. So you can see now that GitHub has triggered that workflow and is going to run all the steps that we defined there. So without the needing to clone this repo, install the dependencies, and run these DBC commands, we can just, from the GitHub interface, update a parameter in the pipeline, and the full training pipeline will be run, and the results will be shared in a PR. This basically allows, pretty much fulfills this set of goals that we have, which is that once a researcher has followed these steps and reached this point, even if he disappears, I can come to this GitHub repository and change any parameters and propose a pull request, and GitHub will take care of rerunning the pipeline without me having to know, without requiring me to know all the details of how this works. So this pretty much fulfills what we wanted, that if a fellow researcher disappears, we can just jump into the project and start to train models. Alternatively, we can also create PRs from a studio by using this run button, which sometimes can be more convenient because you have a nicer interface to edit and see the current values. But this is going to trigger the same behavior as if we change the values from the GitHub interface. Okay. So one thing to notice here is that all this pipeline that we trigger is being run on GitHub servers. So this pipeline that is currently being run is going to be run inside a GitHub machine. And depending on the size of our model and dataset, sometimes this machine might not be powerful enough. So for this example, I choose a very small dataset and a very small model, but probably in many cases you are going to need a GPU or more than one GPU. This is where it comes into play this other feature by CML, which is called SelfHosted Runners. So this feature by CML allows you to create a computing instance in any cloud provider like Amazon, Google, or Azure by Microsoft, and instead of running the pipeline on the GitHub runner, you indicate that you want to run some of the steps on this cloud instance that you have just created.
David, sorry, it's really small, the font. Can you make it bigger?
Okay. So the difference between our workflow in our example and this one is that the first step is going to create a cloud instance with GPU in order to train the model. All the other steps remains the same. So this is a feature by CML called SelfHosted Runners. The link is right here, and you can check it out later. But in this case, because our model is small enough, the training has already finished. Like you can see here, it only took 1 minute and 15 seconds to run the pipeline. And the results are in this PR. So in this PR, we have the report by CML. We have changed epochs from 50, which was the previous state, to 8. And the metrics, well, obviously are worse because we have been training for fewer epochs. So this is our work phase, this current experiment, and this is the one that is present on the GitHub repository. So,
David, can I interrupt you? We have a question.
Sure thing.
So the question is, what's the advantages of CML versus MLOps using Kubernetes, Airflow, or others?
Okay, so I wouldn't say that there are advantages. What I see is different approaches to solve the same problem. So in this case, we are using GitHub Workflows, which are normally used for software engineering tasks. When you use Kubernetes or Airflow, is because you are going to perform some machine learning or data engineering practice. And these GitHub workflows are usually not enough because you need, for example, you need a way to share the artifacts, and that's what DBC Remotes does. And also you need some heavy computing machine, which would be one of your Kubernetes nodes. So in this case, what CML brings as value, for example, with these self-hosted runners, is that we can use the same tools that you use in software engineering, GitHub workflows, and we extend the capabilities in order to add compute in this case, and in order to add a DBC remote to share the artifacts. So you can reuse the same tool that works for software engineering. This, from my perspective, is easier to set up that if you have to set up a Kubernetes cluster or an Airflow scheduler. There are many features that Airflow provides that are not supported by GitHub workflows, but for very basic scheduling, GitHub workflows is just enough.
Thank you.
That's my opinion, but there might be some cases where Kubeflow or Airflow is the right solution for your problem. What I try to show here by using CML and DBC is that you can start from a very simple approach, which reuses the tools that you are already using for tracking your code, and you extend the capabilities. But if you reach a point where this is not enough for you, then it's probably a good indicator that you might need a more elaborated solution like Kubeflow or Airflow.
Okay, so
I think we have a question from.
yeah, it's
Salim.
not the question, but it's he said, so I mean, what are the borders of scalability if using cloud of what you are doing?
Okay, so
What are the borders of the scalability?
okay, so you are limited by GitHub workflows, and I guess it kind of depends on your project. GitHub Workflows allows you to build, for example, what it's called matrix for computation. So you can run multiple runs in parallel. You can run each of those runs, parallel runs in different machines. I guess that I don't know. I have been using this approach of expanding GitHub with DBC Remotes and CML self-hosted runners to train models of, yeah, I would say pretty big sizes and multiple models simultaneously. And I didn't reach the point where this scalability was not enough. And yeah, I don't know, but maybe for a very large company which has to train many models simultaneously, maybe this is not enough. But I have never reached this point because it's pretty much up to you how many machines do you want to use in this case, and it's also up to you which type of instance do you want to set up as a self-hosted runners. Definitely using the default GitHub runner is not enough for training large models, and that's when you need to incorporate this self-hosted runner to get more compute. All right, I
Thank
hope
you.
that answer.
Yeah, so he said thank you. Thanks again.
Okay, so we have come from local reproducibility to shared reproducibility with this GitHub workflow that runs on pull request, but we can even do better and try to make this pipeline run automatically, even if we are not present or on our computer. So this is, for example, this is somehow related with this Airflow question, which is that before we have with the other workflow, we have to manually trigger the training and the pipeline. But GitHub Actions also support to provide custom scheduling, for example, using cron syntax. So here I am indicating that this workflow, which is pretty much the same as before, the only difference is that instead of running on PRs, when a PR is created, it's going to be run at the end of each day. So yeah, the file is pretty much the same. What a minor difference here is that I am using some DBC functionality in order to update the until parameter that we have in our parameters YAML file. So remember that before we have this parameter YAMLs file, and one of the parameters is the boundary, the last date that we want to fetch issues from. So it makes sense if we want to run a workflow daily that we incrementally update this value. And this setParam function from DBC experiment run command allows you to do that. And this is exactly what this workflow does. So at the end of each day, is going to run the pipeline with this command, but is going to update the value of the data until parameter with the current date. So once you merge and insert this workflow in your GitHub repository, every day, so I added this workflow yesterday, sorry, and this is the PR that was generated automatically 18 hours ago, so at the end of yesterday, and it contains all the changes that were produced by updating the pipeline to run with issues from, instead of the 24, the 26, which was the day that started today. So this workflow has the very same syntax as the previous one, but we are using GitHub Actions features for scheduling it in order to run at the end of each day, and we are using DBC run features to update the parameters on the fly. So the only thing that you need to do once you have this workflow run is to accept any of these PRs if the performance has been improved. You can make this workflow more complicated. So in this case, I am only updating the data and I am not doing anything else, but you can implement many more things here. For example, if you want to try some other parameters every week, so you can get as complicated as you want. This is just a very basic example of how to use a schedule to trigger a workflow at the end of each day and generate a new model, which is going to be different because we are going to be fetching data and thus generating a different dataset at the end of each day. So this, I think, covers the goals of the researcher going to vacation and nobody noticing because the model can be retrained, evaluated, and deployed. The only manual step that you need to do is that you have to accept one of these PRs, but that could also be automated inside GitHub Workflows. You could add, for example, a check that checks if the accuracy has increased, and if that's true, then the PR can get automatically merged. So the final step that we would like to do automatically is to deploy the model. So this is another.
Yeah. I have a question. It's my question.
Oh, perfect.
Yeah. So can you show again the GitHub action, the YAML file? Yeah. So when you want to, for example, here runs on Ubuntu. What if you have, it's like you want to test it on Windows or Mac?
Okay. So GitHub by default provides different runners. There are Ubuntu, Mac, and Windows, and you can choose any of those. I don't know if I have one example here, but if you look at GitHub Actions documentations, you will find that you can change this by Mac or Windows, and it will run. Does that answer your question?
Yeah. Can you put also the three of them at the same time?
Yes. For that, you can run. Yes, I think I have an example. For example, we do that in the DBC repo for the tests, I think. Let me look. Yeah, so this is the syntax for defining a matrix that I was mentioning before when discussing Airflow and Kubeflow. So GitHub Workflows allows you to define all these combinations. So any step after this will run in every combination of these lists.
Okay.
So we are using here Ubuntu, Windows, Mac OS, and different Python versions. So all the steps after this we'll try every combination.
Okay, thank you.
In parallel, yeah. Yeah, and yeah, other thing I didn't mention is that here you can provide a custom Docker image if you want, and if you already have the dependencies installed. In this case, I'm using the CML image. That's why I can use DBC and CML even if I didn't install it. So that's the container. Yeah, GitHub Actions and workflows are pretty impressive in my opinion. Another thing to mention is that both CML and DBC are not restricted to GitHub, and you can use it with GitHub, GitLab, and Bitbucket for pretty much every feature. But I personally like GitHub Actions and GitHub Workflows.
And what if you have like data that are, you know, it's like you can put on GitHub. It's like you have to call the data, or you want to schedule like every week, you know, it's like read the data and run a model, and as you explained, but it's like it has to go and look for the data.
Okay, so that would be like an extension of this, which is you could have a separate repository called data registry. Okay, and this is where you would put the static data set. Okay, so instead of having this first stage in our pipeline called get data, what we will do is to use DBC pull or import commands to fetch this data set.
Okay, thank you.
You will first need to push the data set to a DBC remote. But once you have that, then you can import and get from different projects.
Okay, thank you.
Are we good with the timing, by the way?
That's good.
Okay. So the last part of our stuff here, we have reached this point. So Hydia, to elaborate, in this case, like you notice, we are generating the dataset and the model in the same GitHub repository. The difference would be that if you want to have a static version of dataset, you would have a separate Git repository with a DBC remote associated, and you will then use this kind of pattern. That's a good pattern to use if you have multiple projects using the same dataset, or if you have one project using multiple datasets. Okay. But in order to keep the workshop simple, I try to put everything together in a single repository.
Okay, thank you. And so, how about Google Drive, for example, if you have your data in the Google Drive?
Okay, if you have your data in Google Drive, then in an existing folder, then you can set up Google Drive as a remote. This is explained in this document. So in my case, that's what I did. This is my folder where I have the data. And I added this folder as a DBC remote. But yeah, let me share the link in the chat. You can follow that tutorial and similar tutorials depending on your remote.
Okay, thank you. I'm sharing the link.
Okay, thanks. So yeah, we have our Hugging Face train model, but we haven't deployed it yet. So to do that, this is very dependent on your use case, but in this case, what I did was I created a Docker file which uses the Hugging Face Transformers PyTorch CPU image. And the only thing I do here is I copy the training outputs, the outputs that I generate during the train stage, which is the trained model. I copy to the folder model, and I copy a script that I include in this repo, which is called inference. This script called inference, it just uses Hugging Face to load the model, generate a text classification pipeline, and run inference on the given text. So I set up this Docker file, and I create yet another GitHub workflow called deploy model. This workflow I just copy-pasted. I have just copy-pasted it from the GitHub examples. And what it does is that it builds the Docker image using this Docker file and publish the container in the GitHub registry. The important part here is that I first pull the data from my DBC remote, so I get the latest model that has been pushed, and then I build the Docker image with that. So on each commit, I am going to have a different model committed, and I am going to build a different Docker file, Docker image. That action it's deployed on this repo. So every time I create a new commit, it runs the create and publish Docker image. So this image is available as a package in the GitHub repository. So you can run this from any machine and you will get the latest version of the model. If you want, you can have a more elaborated workflow for creating the image using tags for differentiating versions. But in this case, it was just very simple. You have a single image with the latest model that you train. And this image can be used from anywhere with this command. You indicate the path, the URL of the image, and you provide an example input. So our model was trained with DBC issues, and for this example, it was only using the titles of the issue to predict which label it is. So if you provide an example title, it will predict one of the 3 labels that we train the model on. Another option to deploy this model is to create another GitHub workflow. As you can see, you can use workflows for a wide variety of things. So in this case, I create a workflow called issue labeler, and this workflow is going to run every time I open an issue in this repository. So every time I open an issue in this repository, I'm going to run the command that I showed before with the title of the issue that has just been opened. And this is going to predict one of those labels. So I wanted to keep this simple, but you could use the predictions of the model inside this GitHub workflow to automatically assign the label to the issue. Because this is a very simple model and it only covers 3 labels, I didn't deploy the model in the GitHub DBC repository because my teammates might complain. But I added this workflow to this solution repository, and I created an example issue. So I created this example issue with this title, and this triggered the issue labeler workflow, which was triggered yesterday when I created the issue. So this issue, this workflow, what it does is it runs this Docker image that we deploy, and it passes the input as input the title of the issue, and our model predicts that the label that is associated with this issue should be data sync, which in this case is correct because the issue is related to DBC pull commands, and this is the score. So you can try now and go into this repo and create an issue. Let me do that. For example, DBC X run fails when I use JSON input, for example. So if I create this issue, the issue labeler workflow is going to be triggered. Let me put how it looks, this workflow. So this workflow is going to be triggered. Is going to get the Docker image that we have deployed with the other workflow, and it's going to run trying to predict what label is associated to this issue. This can take a while because it's building the Docker image and pulling. So this has just predicted that this issue I just created is associated to the label experiments, which is correct because it is related to the DBC exp run command. And I think that's pretty much it. If you want, you can go to this repo and create an issue and try to see the result in the actions page.
Okay, so maybe let's check if there are questions. So please, can you write if you have any question?
So let me share with you this support page from DBC. So if you have any questions and you want to try DBC, CML, or these other tools, you can go and check the documentation page and ask questions on Discord or via email, wherever you prefer. The Discord community, I can tell that is very active and very fast responses. So from beginner to advanced use cases, feel free to ask whatever you want in Discord, and in less than one day, I can assure you that someone is going to reply.
Thank you. Thank you, David. So please, any question, any issue, please tell us.
I think David explained very well. Thank you.
Thank you very much. I try to keep it simple because there are many things going on. And it's very tricky to try to build something that can fit any use case. So probably this example doesn't fit all the use cases, but it shows how to tie the pieces together. So you go ahead and explore the tools.
Yeah.
Okay, so for beginners, it's like because if there are like some beginners watching us, so what are the resources that they can watch or read, to improve themselves in MLOps or like DevOps or GitHub Actions?
We have just launched this free course from Iterative. I share the link. So it's obviously focused around iterative tools like the ones we use here, DBC and CML, but it tries to cover this MLOps perspective from a very general approach, and it's completely oriented to beginner data scientists that want to start diving into MLOps. So I highly recommend this course because it's obviously made by us.
Thank you.
Yeah, thank you.
Any other question? Okay, I think there are no questions. So thank you, David. Thank you very much for this amazing workshop.
Yeah, thank you. I hope you at least get interested in trying the tools.
That's for sure.
Yeah.
I will try them and I'll let you know. Actually, I want to build a pipeline, for like some work I have, and it will be really helpful for me.
Yeah, like I said, probably Discord is the best way to have immediate answer for any doubts you have. And of course, because it's open source, DBC and all these tools are on GitHub. Feel free to open issues if you encounter some. And I will be happy to try to help.
Okay, thank you. Thank you very much. Thank you, everyone, for attending. Thank you. Bye-bye.
Bye.
Bye.